Hello, welcome everybody to another edition of our Intro to GIS. This time we're going to talk about a module that the title is vector data and map communication. So we kind of have two things here in one, but they really do go hand in hand, and everything kind of flows from where we started to where we get to now. So the attributes are really important, and those should be reviewed before this video, because as we said in at the very beginning, our GIS program is going to have two elements to it: the actual map and then the attribute information. So we're kind of doing this in reverse order, but we're going to start exploring the elements of the map a little bit more now, and that's what this is designed to do. So I'm going to share my screen so I can go over the text with you guys. Okay. And what we're talking about here, when we say maps are a model of reality, maps are considered models. Okay. They're considered some type of representation of reality itself. Okay. And I think we kind of all understand that what a map for all intents and purposes is supposed to be. Let's talk about, when we look at a map, what do we actually pick out? What are the things that stand out with the eyes? When you work in GIS, what is it that you're actually working with? These things that get put on your map. Okay. Well, we call those things features. So general term for saying some type of, and this is a typo, this should be 3.1, some type of event or object, event/object, okay, that is plotted in space. Yeah, so some type of event that's plotted in space, that's a feature, okay, or an object, right? So it's kind of hand in hand. Now, there's a lot of synonyms to this. We could say object, event, activity, form, observation, record. Well, I don't want to say record because that can be a little bit confused, although with the attributes. However, when we say record and we're talking about the attribute table, a single record is also going to correlate to being a single feature in a map. So again, these are the things. If I'm looking at this particular example, every single one of these parcels, every individual singular parcel is a feature. Okay. Every single one of these is its own feature. Okay. Now, these are collectively features. Okay. Plural. So you could have, you could be describing one type of feature, or you could be describing a group of features, meaning more than one. Okay. If you're talking about more than one, then you're generally talking about the same type of event. So in this case, the parcels are features, right? That's one type of feature. Maybe this road or these roads are a different type of feature. Okay. So I want to make one distinction kind of clear here, and that is the fact that features and layers can often be intermixed in the terminology, the terminology we use. I'm probably guilty of it myself. Now, the thing about that is layers and features are technically something different. Okay, so features, like I said, represent that single object, where a layer, or it could be many features, right? But again, we're focusing, when we say feature, we're talking about what is the specific event that we're describing, whereas the specific phenomena we're describing, I think that's actually a better word. What is the phenomena? That sounds fancier and kind of collectively ties things together. Anyways, what is that singular phenomenon? That's feature. Now, a layer could have multiple features contained inside of it or contained within it, right? So when you say layer, you're actually talking about all of the features, right? It could be 10, 20, 100, 5,000, 5 million, who knows? But a layer is going to be a single data file, like a shape file, okay? Shape file is just the Esri or the generic GIS file format type for a layer. But anyway, so layers, a layer contains features. Now, a layer could only have one feature in it. That's fine. So say, you have one record in your layer. Well, that's one feature that's plotted. Then you have another layer that has one specific record. Well, that's a different, feature. But yeah, generally speaking, like if we said, okay, we have a layer for all of the parcels, right? One layer, we're talking about within the GIS now. We're talking about, we have one layer that's all of the parcels. Okay, well, that would be one single data file that contains, several dozen of these green blocks here, right? These green features. If we say we have one layer for all of the roads, for all of the road features, that would be one data file for all of these little pink lines. Okay. And so that's what that's what I just wanted to make sure that you guys understand and know how to distinguish the two different things. Features, when we say features, yes, features would describe multiple events, but usually in the context of one single layer. Okay. I'm going to step away for 1 second. I just got a text that I need to address, and I will be right back. So I'm back. Yeah, just wanted to clarify these differences between layers and features and focus on, in particular, in this case, what do features mean? And when we call that out and we say features, what are we really trying to describe here, right? In this example, it looks like there's 3 different features, technically 3 different layers as well. I should walk that back. There's three different layers with multiple features in each layer, right? So there's a streets layer with multiple features, okay, with more than one feature, as we could see by the attribute table and on the map itself. Buildings and parcels. Street lights. So here's another example of, in this case, we have added another layer with, but think about it though. What's going on here is we have the same feature type, the same representation, although each one is its own feature, right? So each one is its own street light. Bang, 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 bang. All these little red dots, okay? Cool. So the idea of what we're talking about here with this features and shapefiles, these all fall under a specific category within GIS known as vector data, okay? Vector data model, right? GIS is going to represent really 2 different forms of, or is going to present 2 different forms of data. It's going to present data in 2 different forms. That's a better way to say this. Okay. The first and most common way that we're going to think about this, and what you guys have really been working with up until this point and will continue to do, is what's called vector data, okay? The second is called raster data. Raster data is, to kind of summarize, raster data is your aerial photography or some type of 3D, 3-dimensional representation of topography or something like this, right? Generally speaking, those are image files. So like JPEG or .tif or something like this. Whereas your .shp shapefiles, those are vector data types, okay? So we're gonna not address rasters quite yet. That's going to come at a different time. And right now we're focused on the vector part. Vectors, what you guys need to specifically remember, okay? Vectors, they're represented as points, lines, and polygons, okay? So let's get to that in a second. First and foremost, how do we present, how do we represent vectors on the map in GIS? Well, they are, you know, think about these features. So how are they presented? They are either dots. So, okay, you have coordinates. We're talking about maps here now, right? So this stuff is not just created from a vacuum. The intention is that these specific features that are being represented are supposed to be somewhere in the world, right? So like, for example, if it's in San Francisco, there would be a latitude and a longitude of San Francisco. And say you had a street sign in San Francisco that you were trying to represent. Well, the coordinate values, the latitude and longitude of that street sign would then be plotted, okay, would be plotted. And in this case, with a single dot is what I'm discussing as the example, would be plotted on a map. And so what I'm trying to get across to you first and foremost is that that coordinate value is extremely important, okay? So in the text here, we have X and a Y, okay? X and Y is just another way of saying actually longitude, latitude, okay? But yeah, it's a form of positioning features on your map itself, okay? So there's going to be some kind of coordinate value associated with your vector data. So let's see, single or multiple paired coordinates. Let's see, yes. And the thing about it is not just the features locations that where the coordinates are important, but also the feature shape. Okay, the feature shape, right, is determined by or is represented by coordinate values. So yeah, a single coordinate. So a single coordinate, right? Just one single XY or one single long lat or lat long. We call that a vertex. That's an important term, a vertex. Okay, we call that a vertex. If you have multiple coordinates strung together, we call those in the plural form vertices. Okay, so vertex for one, for multiple, we call those vertices. Okay. Let's see. Now, how we, again, represent, when you think of vectors, 3 specific terms should stick in your mind: points, lines, and polygons. Okay, so with points, we've basically already described this part, right? Now with points, okay, points, there are, again, one singular X and Y coordinate. Okay, so one singular coordinate, and then it gets plotted, and then bam, it's like a dot, essentially, is what it is. Okay, so yeah, what kind of features would be represented by points? Well, like I said, street signs, or you know, other types of assets like maybe utility markers, or really anything, right? You could actually do something like a house and have a single point in the center of a house. Depending on how big the map is and what you're trying to represent, you could have a single point to be the central location of, say, something like a building, right? But yeah, generally speaking, something like a point is going to represent, you know, like these type of things: wells, trees, street lights, that type of stuff. Okay. But again, those are not only fixed to those are only examples. Now lines, okay, lines would be a sequence of at least 2 points. Okay, so strung together, right? A string. Think of a string. What does a string do? Well, a string is a line. So think of it like a string of points. Now it could be two together, could be three strung off each other, could be thousands or millions of points strung together. That's going to be a line. Okay. The thing about lines is they can measure length, but they can't measure width. And so, important fact, lines are only one dimensional in that sense. Okay. Now, lines, generally speaking, in terms of vectors, would represent assets like utility, maybe utility wires or canals, roads, streams, railroads. Okay, think about that, right? That kind of stuff is what you would generally see as line features. We call them polylines, okay? But just, I want you to remember lines. Now, polygons, okay, is the third one. And polygons are going to have some kind of boundaries to them. Now, polygons, again, strung together by a sequence of coordinates, okay? The difference is, though, is that they, starting point, so there's a starting point. The starting point of the polygon is also the end point of the polygon, right? And it's represented to be known that there is something inside of that polygon. If you did a line and you just kind of digitize it like this and you closed it at the end, it wouldn't be calculated this GIS wouldn't calculate it to think what's inside of that line, right? It would just calculate the length of it. Whereas with Polygon, because it is known to have an inner part of that, there's also a width involved with this. So length and width, meaning that polygons have a two-dimensional representation, okay? So yeah, polygons. What would be a polygon? Well, think about something like a lake or building outlines, right? Would be good examples. Or hey, how about state boundaries, right? Things like that. You know, those are good examples of polygons. Moving on, okay, topology. This is an important term. Topology. What is topology in a nutshell? Well, topology, because there's this saying that everything is related to everything else, right? And so how do you represent, say, kind of errors or communicate in ways that express where things might cross over one another, or they might butt up against each other, or they might be separated by each other, you know, your features, right? So the science of all of that is called topology. And so when we talk about topology, we're saying we really want to focus on where features are in relation to one another, like I was just describing, and how they are related to one another. Okay, so again, I'll repeat that. Where are the features in relation to each other, and how are they related to each other, right? So it could be in the how are they related, could be something like colors are differentiating the things. But you know, there's three kind of standard principles behind this. The distance between features, right? Differences between features. And so, you know, topology, there's a topology to follow when you're laying out a network of roads. And it wouldn't just be kind of random that they cross at these various places. There's a specific network to how they are outlined, and that is the topology aspect of things, okay? What is that relationship like? Adjacency is similar to what I was just talking about, but with adjacency, we're thinking about, again, the alignment of what creates that network. So let's see, I'm kind of reading this while I'm talking here. The spatial file stored on one point. Well, I'm going to let you guys, again, kind of reread some of this stuff because a lot of this I'm doing as I'm going here. But anyways, the adjacency, and then how are these things connected, right? Connected. So designing these roads, how is the traffic going to flow? And how does that connection, correlate to one another? The overlying thing that I want you guys to remember about topology is, again, the location and relationship of features, more than one feature, one compared to another, right? So it's really, topology is like a distinguishing factor, is what we're talking about, okay? Let's break down now and talk about map communication, right? So we know vectors, how important they are, and generally speaking, vectors are what we think of when we talk about maps, but communicating maps. This is a very, I love this summary of how they describe, what do maps do? Well, they communicate, they obviously communicate information spatially and visually. The other thing about it, maps lie. Maps lie. So how do maps lie? Why do maps lie? Well, there's a little anecdote in here about how are we going to represent, the whole world. Wouldn't that be great if there was a way of having every detail of the whole United States, et cetera, on one big map? And you get into this discussion of like, well, how big can the map actually be? And these kind of, questions like that. And it basically, what we're trying to say here is that when we're communicating a map, the purpose of that, what is the purpose of the map? You're going to ask yourself things like that. What is the purpose of the map? And so that's going to determine, so when we're talking about all maps lie, there's some white lies going to be mixed in there because you can't always represent everything to every detail. There's got to be a selection process and a scaling process to what you're trying to represent, so that it can be communicated in a way that really makes the most sense, right? And is legible for your end, audience to understand. So I'm going to kind of scroll down here so I can try to explain this a little bit better. The cartographic communication process. By the way, cartography is the science by definition, the science of making maps, right? So a cartographer is a map maker. Anyways, so think about the real world, which is what I was just talking about, right? And so, you've got the real world and you're trying to say, how do we represent this place? Like, what is the place that we're trying to represent? Well, that would become the selection. So this is the initial, the real world. Okay, what's possible here? Then the selection is the filtering down to say, I need my map to be of this neighborhood because of the, reasons X, Y, and Z, right? Maybe it's because, they're doing some kind of construction or whatever, right? So the selection process is important. The selection of what and where, to represent will determine, okay, so selection really is extremely important in this communication process. The selection determines the map's purpose and its scale, okay? The selection determines the map's purpose and its scale. So scale meaning how big the map is and how big the things on the map actually are as well, right? How much detail is there? So again, what is the purpose of the map? What are you trying to get across? Who is the audience? I ask these type of questions to myself all the time when I am in the map development, process or mode. These types of questions have to come up. Otherwise, the communication, the map communication, probably will end up being poor, right? So these are like the drivers. These are the drivers of the actual map creation itself, right? Okay, so we get into this a lot more with these examples as you read on here. To generalize a map, to generalize features is a big part of the communication process. So think about, maybe a stream or something. And like I said, it's a string of these various points. Well, a stream probably does something more like this with smoother edges as opposed to very kind of rigid bank kind of line, what a line might look like. So to smooth that feature, right? To smooth that feature, I'm using a term, to smooth that river feature would be a generalization, right? You are, for communication purposes, trying to aesthetically improve the way that that stream looks on the map, okay? So that's one example. And there are other examples here as well. Maybe displace the features, maybe features need to be moved slightly. So in terms of how they lie, maybe there's an accuracy component of that where the map is quote unquote lying to you, or let's say exaggerated features. So if you were trying to really communicate like I don't know, some types of election results in specific areas, and you wanted to exaggerate minority demographics, or you wanted to just exaggerate demographics in general, right? And so you would exaggerate, say, features, the features that represent, the higher ratio of one demographic versus another, right? So that's to say, the scale in that case is not representative of, this is not a great example, but the scale is not representative of, the real world in that case. However, for communication purposes, it makes sense to do something like that, okay? So that's what these examples are here, okay? Again, there's a lot in this section that talks about this. The primary role of maps is to communicate, actually. And so without selection, this is important, without selection and generalization. So let's see. Oh, conventions. I do want to talk about conventions quickly here. Conventions would be something like kind of universal, a universal understanding of specific features, right? Now, you'd say green means good, red means bad, right? Those are kind of societal conventions, and those can be communicated on a map where, generally speaking, those are interpreted quite easily. Nevertheless, not all conventions, there's not a long slew of conventions for the general public. But say maybe it's a workplace and they have a standard color scheme of various features that they like to use. So roads are always brown and rivers are always blue and whatever, right? So there could be thousands of these different things, but the whole point is, here's a convention of these features, and we'll use that for always communicating, when we're putting our maps together, right? Okay, continuing on. Let's close here with talking about different map types. Okay, map types. Now, generally speaking, we say, okay, there are two map types that you're going to be working with and again, this is based on purpose. Really, it's going to be, the purpose is going to drive this. So is it a general purpose map? Okay, is it a general purpose map, which is, shows locations of roads, rivers, institutions, really more for general purpose, is not something that's, I guess we could say, more of a presentation at the end kind of aspect. That would be more for a data analytics component, general purpose maps. So like, for example, I need to find, the selection or answer some questions about or plot out without making it really pretty, but I need to plot out, I don't know, locations of McDonald's or something like that, right? Whatever it is. So again, that's going to be more on the data side, on the GIS professional side, where you're going to be working in that general purpose range. Now for the next type is called thematic maps. So there's a theme. Thematic maps depict something particular. So that's what I meant by the purpose is the driver there. So maybe the purpose is to depict population density or age distribution, income, something like that, right? So maybe the map starts out general purpose and kind of the foundation of it from the data analyst perspective is general purpose, but then the end result is to have it be thematic that can communicate something very specific in particular. Now, there are different types of thematic maps for describing various things or representing various things. The dot density here, okay, with a dot density, what's going to happen is you have points that are all the same size, okay, all the same color, right? There's really no differentiation between the points themselves, but the amount of points within a specific area, like in this case, we have, states. And so say it represents, I don't know, income levels. Or actually, here's a better example. Say the dots represent the amount of fast food, right? The amount of fast food locations, right? Notice I didn't say the amount of one specific brand or something, but the amount of fast food locations in a state. Now you might go, well, I'm looking at California. There's more than 10 fast food restaurants in California. So the point is not to say that each dot represents each individual feature, but each dot represents some type of value, some type of let's see. Yeah, so could represent 500 restaurants. Each dot could represent 500 restaurants, or 500 fast food locations. And so kind of mathematically speaking, that's what we're trying to demonstrate here. It's more about the density of what's on the screen as opposed to the overall number itself. But yeah, you would see something like in this example, here's a density of, fast food is more, there's a lot more of it in the Northeast, right? That could be also because the states are smaller. But anyways, that fast food is just an example. I don't know if that's the truth or not. Isoline maps are, again, you're representing something that is a distinguishing feature, right? A distinguishing feature. And so this could be a temperature. These could be temperature. These isolines could be temperature, like for example, or air pressure, right? You might see something like this on the weather report, which is common. But like, for example, this could be 900 pressure, 950, 1000, 1500. So ISO lines generally have a regular spacing between them, right? In terms of the numeric values. And the lines represent the actual locations and kind of like a pattern of where those things go, and also how to separate and differentiate between one place to the other, right? Topography is another big one when it comes to isolines, because these are very commonly represent elevation values, right? Elevation values, especially if you look at something like a trail map or something like this, right? And you see these lines like that, those are representing the elevation contours of that area. Next, we have, let's see, graduated symbols. So this is similar to what we were talking about earlier. Look down here, okay? Except in this instance, though, we have one specific dot, within, let's say, the states here. And again, maybe it is fast food again. But what we've done now is we've said, okay, the amount of the amount of those fast food locations is going to be represented as either, the bigger the dot is, the more fast food locations there are, is kind of in a simple way of describing that. So yeah, the map doesn't get too cluttered with a whole bunch of dots, densely populating various places, or not at all. Instead you have single thing representing every single field in this case, and then the amount of records there are would determine the size of the actual dot itself. Okay, so that's a graduated symbol map. And between this one and this one, because there's some confusion there, I would say that this is a much more common map type to find. Okay, personally, I think it communicates things better, but kind of depends on, again, what's the purpose. So chloropleth is another very common map type. And in this instance, what we've done now is we're really evaluating a range of, something. So like representing that by a shade of color. And so, yeah, what we're trying to say is the darker something is, generally speaking, the rule is the darker the color is on the map, the more of that specific value, that we're trying to evaluate exists. So again, maybe it's fast food. And so in this case, we say, oh yeah, the darker ones mean that, we don't have the locations or anything like that plotted here, but we can pretty easily determine that on the West Coast, there's a lot more fast food locations, and it could be per, 100 miles, per 100-mile radius or something like that. I don't know. But anyways, you see this commonly with like elections, the election, and really represents quite well, because we're focusing it on specific, like in this instance, the states, and what's going on in the states, and what part of the country, how much differentiation in the range are voting either Democrat or Republican, something like that, right? So this is chloropleth. Cartogram is an interesting one. What cartogram does is we take the features of interest and exaggerate them, right? So this is a form of what did we say? Yeah, exaggeration, generalization, right? So we exaggerate the features based on, again, some criteria. Maybe this is again, states that voted for Democrat, right, over here in the election. Well, these are not to scale anymore. You could have cartograms where the features are close to one another and connected to one another, or they could be spaced apart. I kind of like them spaced apart because sometimes the features are going to be really big and sometimes they're going to be really small. But it can just get kind of busy if they're all clustered together like this, or clustered together and not like this. But anyways, yeah, the idea is to, just looking at this map, right? California is a big state, but Texas is also a very big state. Texas is actually size-wise much bigger than California, okay? On this map, however, you wouldn't necessarily know that. But what's the purpose? Well, we're trying to communicate what percentage of the population, in terms of the states, which ones were voted, Democrat in this example, right? Well, and California is going to have a lot more of those votes as opposed to Texas. And that's what we're trying to describe here. Flow maps, okay, a flow map here is going to be lines. Generally, you're going to have lines depicting direction of something. So there might be an epicenter or a few epicenters, but direction and also magnitude, like how strong is that, or how many of, like, say this is a airplane route map. Well, first and foremost, you get the locations of, say, from New York to all these various other airports. So that's the first thing that is outlined there, right? But maybe the darker line here means that there are 10 flights from New York to, I'll just say, LA, right? From New York to LA. But from New York to Phoenix, there's only one, right? So see that this is a thinner line. So its line thickness is the magnitude in that instance, okay? And then last we have, as our example, we have density maps. So density maps are similar to the dots, except in this case, we're not just using individual, we've now kind of, imagine if each dot was its own, I don't know, little container of fluid or something, and then we kind of smashed it and all that little fluid kind of dripped out like that, right? So in this case, we have kind of a more spread out version of the density, right? And so the more of the fluid there is, the more dense the features are in this case, right? This is also commonly mixed up with what's called a heat map. And so, you could have a density also not just represented by one specific color, but you could have a couple different colors. And so, like, say red, meaning, you have more features, and the red one would probably be, like in this case, well, the more fluid is there, whereas the blue would be kind of less fluid and a blue color. Anyways, I think you get the idea, right? It's not that hard to kind of contrive this when you see what it looks like. I want you guys to know, based on the pictures here, I might ask you on a test, based on the picture or based on a description, what type of map is this, right? Or vice versa, right? So, okay, those are all different types of thematic maps for you guys to think about. And that's it, actually. That's it for this one. Yeah, a lot to discuss here, but we're getting through it. And that's all I have for today. Thanks for watching. Okay, bye.